Hello and welcome to this edition of the Gen Z tutorial video series. This is one of a series of videos that will introduce Gen Z, what it is, what problems does it solve, and what are some of its high-level attributes and capabilities that make it a powerful solution for next-generation infrastructure. This video series is made in three parts. Gen Z, a new approach, introduces the challenges faced by today's infrastructure and why Gen Z offers an opportunity to drive new levels of innovation. The Gen Z Tenets provides a list of the architectural tenets that drove the design, protocol definition, and specification of Gen Z. And finally, there are a series of videos for a number of Gen Z use cases, which are examples of how to apply Gen Z technology into various real-world infrastructure components and solutions. Today we present the Gen Z tenets. So, let's get started. This module describes the key tenets used to define the requirements for the Gen Z technology. They include being open, high performance, reliable, secure, flexible, compatible, and economic. In today's video, we'll be covering each of these in turn to look how Gen Z embodies each of these tenets. The first Gen Z tenet is open. That is, it has always been the intention that Gen Z be a completely open standard. So much so that not only software frameworks and APIs are standardized, but even reference designs for the Gen Z interface hardware are shared among consortium members. So what is the Gen Z Consortium? Gen Z is backed by broad industry support with over 40 members of the rapidly growing Gen Z Consortium. This consortium was established to develop the Gen Z family of specifications, standards, implementation profiles, and use cases. The consortium also provides for the general sponsorship and support for maintaining Gen Z as a completely open and ubiquitous technology. The members of the Gen Z consortium represent component suppliers, hardware and software intellectual property development companies, connector and cable suppliers, OEM and system vendors, subsystem vendors, and software companies. Taking a closer look at the components that can be delivered as part of a Gen Z infrastructure ecosystem, these can include CPUs, both server, client, and embedded, graphics processors, that is, GPUs, special purpose processors like digital signal processors or DSPs, storage controllers, switches, gateways to legacy networks and fabrics, FPGAs, DRAM memory, flash memory, and a wide variety of storage class memories, including phase change, resistive RAM, spin transfer torque, 3D crosspoint, etc. Because Gen Z is an open standard that includes software frameworks, APIs, reference hardware designs, and use cases for various solutions, it embodies an environment of innovation that enables Gen Z to be applied to a wide variety of components, systems, and solutions, far beyond what can even be envisioned today. The next Gen Z tenet is high performance. Gen Z was designed to be high bandwidth and low latency, and to do it at scale, from motherboard to chassis to rack and row scale. Bandwidth to feed the ever-increasing core counts and processors of the future, but more efficiently, with less power and cost than the trajectory of technology evolution we are on today. Gen Z was designed to be a high-bandwidth universal system interconnect. It handles load store memory accesses, block access storage, and messaging. The chart on the upper right depicts the full duplex aggregate bandwidth in gigabytes per second for several different Gen Z configurations of varying numbers of lane pairs, where a lane pair is one transmit plus one receive lane, and lane data rates. We will consider two scenarios that represent how Gen Z may be introduced in a typical server deployment. Initially, Gen Z will not be integrated into the CPU, but will use an external bridge that provides connectivity between the CPU's high-performance interprocessor or cache-coherent links and the Gen Z links to the rest of the system. A typical bridge configuration would be 32 Gen Z lane pairs and supports either 25, 32, 56, or 112 gigatransfers per second data rates, depending on the generation of technology and markets and workloads being targeted. The bandwidth that can be achieved with this solution are illustrated in the four leftmost bars in the chart. These bandwidth numbers are impressive considering that 5 DDR5 memory channels operating at 4,400 megatransfers per second yields about 282 gigabytes per second of raw bandwidth in comparison. The Gen Z links can support byte addressable memory, block access storage, I/O to accelerators or gateways, and messaging to other servers through external Gen Z fabrics of various topologies. Note, although DRAM is shown, storage class memory or SCM will be more common as the byte addressable memory for an external bridge. If the solution requires more than 32 lanes, adding external Gen Z switches to expand the connectivity will be common. Over the course of time, GPUs or other system on a chip or SoCs will integrate the Gen Z bridge logic to provide native Gen Z link support. Watch the animation to see how this integration transforms, simplifies, and expands the Gen Z connectivity of the CPU. Now, the number of Gen Z lane pairs that the CPU supports can double or more. We demonstrate this by using 64 lane pairs for a typical CPU configuration, which corresponds to the rightmost bars in the bandwidth chart. Future CPUs and SoCs may even support more Gen Z lane pairs. Our diagram also changes to illustrate that the greater number of Gen Z links, we eliminate the external Gen Z switch to allow direct attachment of all the Gen Z peripherals. We still have links available for connectivity to external Gen Z fabrics to facilitate sharing resources and messaging between systems. Furthermore, integrating the Gen Z logic also enables the very highest bandwidth and very lowest latency such that high-performance DRAM attachment can be achieved, even as a replacement for traditional DDR channels. For those viewers who prefer to see bandwidth numbers in networking terminology, here is the same chart that uses terabits per second for aggregate bandwidth. Based on the roadmap of linked data rates, one can see that Gen Z offers the memory, I/O, block access, and messaging bandwidth necessary to feed the hungriest workloads in these high core count CPUs. Gen Z also offers high-performance, low-latency access to byte-addressable storage class memory, or SCM. This storage class memory can be connected directly to a processor or is resident on a Gen Z fabric to which processors are also attached. This is accomplished using technology that is already being implemented in operating systems today, the Persistent Memory File System, or PMFS, also known as the Direct Access File System, or DAX file system. This software was developed for use with non-volatile DIMMs, or NVDIMMs, so that they did not have to be treated as storage devices with all of the storage software stack overhead. The file system enables applications to use a modified file access API to have file data directly mapped into its memory space so that it can be operated on using CPU load store byte addressable instructions for incredibly low latency file data access. By simply using a Gen Z storage class memory driver instead of an NVDIMM driver, Gen Z attached storage class memory can take advantage of this technology with no changes to the operating system. The animated figure on the right demonstrates the stark difference in performance of block storage under a traditional software stack and storage class memory under the persistent memory or direct access file system. Let's say our application wants to access a couple of bytes at a certain offset in a file that hasn't been prefetched into buffer cache. In the case of a traditional storage software stack on the left, the access request initiates the execution of approximately 25,000 instructions on the CPU while initiating a total of 5 different data buffer copies in the different layers of the stack. The same request, initiated through the PMFS or DAX file system, initiates an execution of 3 instructions on the CPU and no data copies to read-write a small number of bytes directly from the storage class memory. And oh, by the way, we didn't make this timing of this slide unfair, because we'd have to wait all day long for the animation to complete if we were going to make this to scale for the traditional storage software stack. So Gen Z enables low latency data access to storage class memory deployed in a variety of flexible topology options while using operating system software proven for use with today's NVDIMM technology. Gen Z also offers a set of features that are critical to the proper handling of mixed-use load store memory accesses and bulk data accesses and messaging as a universal interconnect and fabric. Have you ever been driving your car on a 2-lane road and you're in a hurry and you get stuck behind one of those large trucks that you can't do anything about it? It's frustrating, isn't it? Well, this is a lot like traditional networks today, where low latency message packets or small file data access packets get stuck behind one or more large packets that are part of a bulk data transfer. The larger the maximum packet size supported, the worse the problem is. Once a port starts transmitting a large packet, if a small low latency packet is ready to go, too bad. Traditional networks have some decent amount of quality of service capabilities, and there's modest link aggregation and multipath support. But many of these features require software to support them. For example, link aggregation drivers in an operating system. Just like our 2-lane road, traditional networks have always been challenged with mixed-use data access and messaging. These problems are compounded if we try to overlay CPU load store accesses to byte addressable memory over networks like these. Gen Z, on the other hand, is effectively a multi-lane superhighway. With its multi-link and multipath technologies, Gen Z effectively provides multiple traffic lanes through the fabric. In addition, each link supports up to 32 virtual channels that are individually flow controlled and can be used for quality of service and traffic class prioritization, ensuring transaction progress at all times under any traffic condition or congestion. Furthermore, Gen Z utilizes a 256-byte maximum packet size coupled with hardware segmentation and reassembly for large data transfers to ensure proper interleaving of small, low-latency traffic with large bulk data access operations. The animated figure on the bottom illustrates the fact that fabric management can provision combinations of links, paths, and virtual channels for different classes of traffic. Each lane of traffic in the diagram actually equates to a combination of Gen Z links, paths, and virtual channels. You will notice that there are no 18-wheeler trucks anymore, as the Gen Z components segment and reassemble large data transfers into smaller 256-byte transfers. In the figure, some lanes are dedicated to mixed, small, and bulk traffic loads. This is shown on the lower 2 lanes going in each direction. In a similar manner, the top lane in each direction carries only low latency packets for CPU load store byte addressable operations, for example. The next lane down in each direction is dedicated for bulk data movement. The reliability aspects of Gen Z allow traffic classes to be assigned to more than one link and path in order to facilitate alternate paths in the event of link or component failures. We will talk more about this a bit later in this video. These slides give a sample of the kinds of capabilities that have been designed into Gen Z and its specification to facilitate higher levels of system and solution performance. The next Gen Z tenet is reliable. If we'll be accessing memory resources over a simple point-to-point interconnect or over a complex fabric at distance over any type of cabling system, we need to be able to provide rock-solid reliability to ensure no single points of failure and availability to support adds, moves, and upgrades to the fabric without disruption of basic load store or bulk data accesses. Reliability, availability, and serviceability are key capabilities integrated into the Gen Z technology. Let's take a look at a few examples of these capabilities. Gen Z supports native multi-link capability on every component. In the figure in the upper right, you can see that Gen Z components are not subject to the single link connectivity restrictions between each component, such as exist with today's DDR memory channels or PCI Express links. In that figure, a graphics processor unit or GPU is connected to a CPU or SoC with 4 parallel Gen Z links. Instead of having a single by 16 PCI bus connecting these components, Gen Z enables 4 by 4 links to be employed. Why is this beneficial, you might ask? First, this is one of the mechanisms Gen Z uses to create the superhighway of interconnects we described in the high performance portion of this video. But the other reason to do this is to enable a level of reliability not seen in most memory or I/O channel technology today. The animated figure on the bottom left demonstrates traffic flow if all links are working properly between two components. The integrated Gen Z logic within the components distribute the memory and I/O transactions across these links, load balancing the traffic according to policies established by fabric management. The animated figure on the bottom right illustrates the case of a link failure. Let's say one of the links goes down. The components will automatically load balance the traffic that would have normally transited the broken orange link and redistribute this traffic over the remaining operational links. This failover operation is performed completely in the Gen Z hardware and does not require operating system software or drivers to provide this functionality, like a traditional LAN or storage network. Once the orange link is restored, the Gen Z hardware automatically rebalances the traffic across the links. This is a standard feature of Gen Z, and so this capability is universal for different component types like CPUs, memory, storage, accelerators, etc. Again, a key attribute is that this feature operates over unmodified operating system with no additional software required. Gen Z also supports a multipath feature that is similar in operation as multilink, but applies to any arbitrary path through a switched Gen Z fabric of any topology. As illustrated in the figure at the upper right, instead of connecting parallel links between the same components, one or more links are connected to one switch, and one or more links are connected to other switches. Now, there are multiple paths between components over which traffic transverses, different switches. Again, to support Gen Z as a superhighway for mixed traffic types, traffic management uses these multiple paths to establish traffic policies for steering various traffic classes through various redundant paths through the fabric. For fabrics composed of Gen Z switches, this feature also enables a level of reliability not seen in most memory or I/O channel technology today. The animated figure on the bottom left demonstrates traffic flow if all links and switches are working properly between two components that are connected through two links, one through each of two switches. The integrated Gen Z logic within the components distributes the memory and I/O transactions across the links, load balancing the traffic according to policies established by fabric management. The animated figure on the bottom right illustrates the case of a switch component or link failure. Let's say one of the switches goes down. The components will automatically load balance the traffic that would have normally transited the broken switch path at the bottom and redistribute this traffic over the remaining operational path at the top. This failover operation is performed completely in the Gen Z hardware and does not require operating system software or drivers to provide this functionality, again, like traditional LAN or storage networks. Once the bottom switch is restored, the Gen Z hardware automatically rebalances the traffic across all paths. This is a standard feature for Gen Z, and so this capability is universal for different component types like CPUs, memory, storage, and accelerators, etc. Again, a key attribute is that this feature operates over unmodified operating systems with no additional software required. Let's consider another topology that is used for the lowest latency connections, point-to-point mode. Gen Z supports the ability to daisy chain point-to-point connected components, as illustrated in the figure at the upper right. Why are daisy chains useful topologies? If we have a CPU or an SoC that has a limited number of point-to-point link interfaces, we can still daisy chain multiple components, such as memory or storage, to provide higher capacity but sharing the bandwidth of the links from the SoC or CPU. This is an ideal configuration for slower storage class memory or storage devices. This figure on the upper right depicts an SoC with 3 redundantly connected daisy chains, one with DRAM memory, one with storage class memory, and another with storage devices like Gen Z SSDs. Redundantly connected daisy chains have both ends of the chain connected to the SoC. The animated figure on the bottom left illustrates traffic flow if all links are working properly between an SoC and a couple of components, for example memory, configured to a double-ended daisy chain topology. The integrated Gen Z logic within the components distribute the memory and I/O transactions across the links, load balancing the traffic according to policies established by fabric management. In this case, these policies would tend to favor the links with the lowest number of hops to get to the target component. The animated figure on the bottom right illustrates the case of a link failure. The components will automatically reroute traffic that would have normally transited the broken link via paths that use more than one hop through intermediate components to reach the destination component. This failover and rerouting operation is performed completely in Gen Z hardware and does not require operating system software or drivers to provide this functionality, again, like traditional LAN or storage networks. Once the link is restored, the Gen Z hardware automatically reroutes the traffic in an optimal manner based on the original traffic management policies. This is a standard feature for Gen Z, and so this capability is universal for different component types. Again, CPUs, memory, storage accelerators, etc. The key attribute of this feature is, again, it operates over unmodified operating systems with no additional software required. These are examples of just some of the Gen Z features and functions that provide leading-edge reliability. The next Gen Z tenet is secure. For data-centric computing, we can place a variety of memory and compute components on a common fabric. The data stored in the memory will be operated on by the compute components. This environment can be composed of multiple workloads in a multi-tenant manner. The data stored in this fabric-attached memory needs to be protected with rock-solid security to prevent inadvertent or malicious access to data in various memory components, or even a specific region of a memory component by unauthorized applications or workloads. Gen Z offers many different security and partitioning capabilities. Today, we will focus on 4 of these and cover the others in another video tutorial on advanced security capabilities at a later date. Here are some features that make Gen Z secure. The first security feature are access keys, which allow Gen Z fabrics to be logically partitioned where each component and each link can be associated with one or more access keys. One can think of access keys as similar to virtual LANs or VLANs in networking. The animated figure on the bottom left illustrates a simple example of the use of access keys. Access key protection is enforced in Gen Z switches, either those integrated into any component or standalone Gen Z switches as shown here. When a component sends a Gen Z packet, it can include an optional access key in the header. When a Gen Z switch forwards a packet with an access key field, it validates that the destination link has been configured with the same key. If not, the packet is dropped by the switch, an access violation audit log entry is created, and a security event is reported to fabric management by in-band or out-of-band mechanisms. This allows fabric management to quickly identify the issue and determine whether it was an inadvertent configuration error or a malicious attempt to try and access the target component. In our example at the bottom left, component A sends a packet with a green access key to component C, while component B sends a packet with a purple access key to component C. The link to component C has only been configured with a green access key. So the switch processes the packet from component A and forwards it to component C because the keys match. The switch, on the other hand, validates that the keys do not match from component B to component C and thus drops component B's packet, adds an access violation entry into the audit log, and issues a security event to fabric management. The next security feature are memory region keys, which are designed to protect components that share their memory regions on a Gen Z fabric. Typical components that share their memory will do so by sharing multiple memory regions to different components on the fabric, those typically being compute components or using these regions. The use of memory region keys ensures proper partitioning and protection to prevent components from unauthorized access to memory regions shared on one or more fabrics. When a component sends a Gen Z packet, it can include an optional memory region key in the header. When a component that is sharing one or more memory regions receives this packet, it validates the targeted memory region is protected by the same key present in the packet header. If not, the packet is dropped, an access violation log entry is created, and a security event is reported to fabric management by in-band or out-of-band mechanisms. Again, this enables fabric management to quickly identify the issue and determine whether it was an inadvertent configuration error or a malicious attempt to try and access the target component's memory region. Notice that in the case of memory region keys, the validation is performed by the component that owns the memory resources, not the Gen Z switches, as was the case in access keys. In our example on the bottom right, component C is configured to share a green memory region with a green memory region key to other components on the fabric. Component A sends a packet with an address within C's green memory region and a green memory region key to component C, while component B sends a packet with an address in C's green memory region but has a purple memory region key. Component C accepts and processes the packet from component A because the keys match. Component C drops the packet from component B, adds the access violation entry into the audit log, and issues a security event to fabric management because the keys do not match. Gen Z also provides cryptographic security capabilities for authentication and anti-replay prevention. Components that require authenticated communication with each other will share a secret key called a transaction integrity key, or TIK. The transaction integrity keys, which are relatively large keys, for example, 256 bits, are distributed to the components in a secure manner using industry-standard key wrapping techniques by out-of-band or in-band management mechanisms. When a Gen Z packet is generated and sent, each component uses the appropriate transaction integrity key and the Gen Z packet contents to calculate a secure hash-based message authentication code, or HMAC, that is inserted into an optional header in the packet. When the packet is received, the destination component calculates the HMAC from its transaction integrity key and the Gen Z packet contents. If the HMACs do not match, the packet is discarded, an access violation audit log entry is created, and a security event is reported to fabric management by in-band or out-of-band mechanisms. Again, this enables fabric management to quickly identify the issue and determine whether it was an inadvertent configuration error or a malicious attempt to try and access the target component. In our example in the bottom left, component C is configured to use the green transaction integrity key for secure authenticated communication to the fabric. Component A sends a packet to component C with an HMAC inserted that was calculated using the green transaction integrity key. Component B, on the other hand, sends a packet to component C with an HMAC inserted that was calculated using its purple transaction integrity key. Component C accepts and processes the packet from component A because the sent and calculated HMACs match. Component C drops the packet from component B because an access violation entry into the audit log and issues a security event to the fabric management because the sent and calculated HMACs do not match. Closely related to the HMAC capability is the anti-replay tag used to prevent man-in-the-middle attacks where components may repeat previously sent packets for the purpose of impairing a target component. Components that require anti-replay protection must also support the hash-based message authentication code, or HMAC cryptographic authentication we just discussed. There are two types of anti-replay tags that can be supported: either a packet sequence number unique to the source and destination component, or a master clock value driven by the Gen Z precision time feature. When a Gen Z packet is generated and sent, each component calculates the next per destination sequence number or master clock value and inserts this in the anti-replay tag field. The component then generates the HMAC security encrypted hash-based message authentication code and inserts it in the packet header. When the packet is received, the destination component performs the HMAC validation described previously. Then it checks the sequence number or master time for proper forward progress, and if not valid, the packet is discarded, an access violation audit entry is created, and a security event is reported to Fabric Management by in-band or out-of-band mechanisms. Fabric Management can use this to determine the presence of a faulty component or man-in-the-middle replay attack. In our example, on the bottom right, component A and component C are configured with green transaction integrity keys for the secure authenticated communication in the fabric. Component A sends 3 packets to component C with an HMAC and a sequence number based anti-replay tags of values 1, 2, and 3, respectively, inserted into the headers. Component B is a man in the middle that passes packet 1, 2, and 3, but duplicates the second packet. The component C receives, validates, and accepts the first 2 packets, but it detects a replay of packet 2 and drops the replayed packet, adds an access violation entry into the audit log, and issues a security event to Fabric Management. The third packet is processed and accepted as it meets this next sequence number in the anti-replay tag. Note that tampering with the contents of the anti-replay tags is prevented by the hash-based message authentication code validation of the entire packet. Again, these are just a sample of the features that make Gen Z secure, and others will be covered in the future as you read about them in the Gen Z core specification freely available on the Gen Z Consortium website. The next Gen Z tenet is flexible. Gen Z was designed to be very flexible protocol to support a wide variety of interconnects, configurations, and topologies. Let's look at some examples of Gen Z's flexibility. Gen Z offers the most flexible link configurations available today. First, the differential signals, or a lane, can operate anywhere from 16 to 112 gigatransfers per second per lane. A Gen Z link can be composed of 1 to 256 lanes, or differential pairs, although 8 lanes will be a common configuration. Gen Z can support both symmetric and asymmetric links, which is unique in the industry. The animated figures on this page helps explain how symmetric and asymmetric link configurations work. The figure on the left demonstrates several symmetric link configurations which have the same number of transmit and receive lanes. The figure illustrates a by 1, by 2, by 4, and by 8 lane pairs, or transmit-receive pairs, between 2 components. Symmetric links are good for general-purpose use cases where the read-write bandwidth on the link is about even or perhaps is unknown. The figure on the right demonstrates the difference between a by 8 transmit and by 8 receive symmetric link and A by 2 transmit and a by 14 receive asymmetric link. Asymmetric links are beneficial if traffic flowing over the link is biased for reads or writes. For example, if a CPU is connected to a memory component and the workloads will be read-centric, where most of the data is sent from memory to CPU, then having a receive-heavy asymmetric link from the CPU perspective is important. From the memory perspective, this is a transmit-heavy asymmetric link. A Gen Z physical interface can be designed to support dynamically configuring the links between symmetric and various asymmetric modes. Gen Z supports both copper and optical interconnects. Gen Z core specification specifies a general physical layer abstraction interface to support a variety of physical layers. The Gen Z physical layer specification calls out both PCI compatible physical layer interfaces as well as IEEE 802.3 or Ethernet physical layer interfaces. We will talk about PCI compatible physical layers in the Gen Z compatible portion of this presentation. The Gen Z physical layer specification calls out 3 variants of the IEEE 802.3 standard physical layer, where each one varies by electrical link budgets and power consumption, from short reach low power to long reach high power options. Gen Z is the universal system interconnect. In the animated figure to the right, we have an SoC, for example a CPU, that is connected to an external Gen Z switch. Any type of Gen Z enabled component can be connected to any Gen Z link. We don't have dedicated memory links or I/O links or storage links. Any link can be used for any purpose for access to memory, I/O, storage, or even other compute components for the purpose of messaging or data sharing. This capability allows very fluid deployments so that if we have an I/O-centric workload, I can add more accelerators to my configuration. If I have a memory-centric workload, I can add more memory to the system. If I need more storage, I can place storage components on any available link. Basically, one architecture that can support a wide variety of deployment models and workloads. In other words, we can right-size the infrastructure around a common architecture, which is very powerful. Gen Z's flexibility is evident in its support of a variety of topologies and scales of deployment. Gen Z's flexible physical layer options and capabilities enables Gen Z to scale from a simple component-component interconnect in a local system all the way to rack or row scale deployments. The figures at the bottom of this page illustrate the various scales of deployment that Gen Z enables, along with the associated physical layer and topology options available. The figure at the bottom left is an example of a local system depicting a server motherboard that has CPUs that connect to DRAM or storage class memory using Gen Z daisy chain topologies. This configuration utilizes low-cost copper interconnects that can employ either PCI or IEEE 802.3 physical layer technologies. In either case, Gen Z enables flexibility in the placement of memory as seen in the example motherboard. DRAM and storage class memory can be placed anywhere on that motherboard and is not restricted to being placed near the CPUs where space and thermal issues abound. New custom form factors can be employed for new innovative solutions like high-capacity memory modules. Local system deployment can also utilize simple point-to-point or switch topologies for memory or I/O expansion in a similar way that PCI Express switches are used today. The next figure from the bottom left is an example of a system in a chassis or enclosure where one or more CPUs, accelerators, DRAM, and storage class memory, etc., are connected to a mesh fabric topology using Gen Z. This configuration is possible because the standard Gen Z logic blocks include integrated switch layers that allow not only point-to-point communication, but also multiple paths through a fabric by taking second and third hops through other components. Other topologies that don't include external switches can be supported, like Torus 2D and 3D configurations. This deployment model supports low-cost copper interconnects where DRAM, storage class memory, and accelerators like GPUs and FPGAs can be placed in the same locations that small or large form factor disks or SSDs are placed today. In addition, new custom form factors are possible, like large form factor memory modules or accelerator bays that again fit where one would typically find storage drives today. These modules can support hot plug capability to enable fast replacement of failed components. The third figure from the bottom left is an example of a rack scale deployment using Gen Z as a traditional topology with a redundant external Gen Z switches at the top of rack. However, the mechanical structure presented is anything but traditional, in that a rack of universal slots is used to host CPU, GPU, FPGA, DRAM, storage class memory, gateways, or any other type of Gen Z enabled modules. The Gen Z interconnects can be copper or optical in this case, will probably be based on IEEE 802.3 physical layer technology to span the rack scale interconnect distances. This configuration supports a variety of other topologies like torus 2D, 3D, spine leaf, etc. This example represents the dawn of a new era of composability we will discuss later in this presentation. Finally, the figure at the bottom right illustrates a row scale deployment using Gen Z. Gen Z's explicit class of request responses support well over 200 million components on a single fabric, enabling a row scale deployment shown at the bottom. This deployment scale typically employs fabric topologies used in high-performance computing or HPC environments, such as fat trees, CLO, Dragonfly, Hypercube, HyperX, you name it, Gen Z can support it. These topologies employ multiple tiers of external Gen Z switches, which have extremely low latencies in the tens of nanoseconds. The Gen Z interconnects in these topologies will typically use IEEE 802.3 physical layers and optical transceivers or integrated photonics to support the distance required for row scale deployments. Row scale deployments build on the universal slot concept presented at rack scale and bring to life the true power of next generation composable infrastructure. Looking closer at the modular deployment models presented in the rack and row scale solutions illustrated on the last page, Gen Z enables different classes of modular shelves that offer special purpose methods of combining modules together, yet work seamlessly on the same fabric. The figure on this page depicts three modular shelves that can be used for rack row scale solutions. The top shelf is a heterogeneous compute shelf that supports a variety of module types and sizes. The second shelf depicts a compute shelf with CPUs, GPUs, and FPGAs of various types. The bottom shelf is an example of a memory media shelf that supports a variety of memory media module types, including DRAM, storage class memory, and flash memory modules. This enables the ability to compose logical infrastructure from these shelves, as we will see later. The final aspect of Gen Z's flexibility is its connector system based on the TE sliver connector family. The pin density is 0.6 millimeters and much smaller than legacy connectors, but with excellent signal integrity characteristics, demonstrated with performance to 112 gigatransfers per second. This family supports vertical connectors of various sizes for both drive, similar to the U.2 connector, or cards, similar to PCIe, form factors. There is also a compatible right angle and straddle mount connectors as well. There are also copper and optical cable connectors in this family. The strengths of this connector system have led to its adoption by the Gen Z consortium, but it is also being considered for adoption by the EDSFF, SNIA small form factor, PCI SIG, and OCP MES standards bodies in our consortia. Enabling the TE sliver family as a multi-purpose connector helps drive volumes and lower costs. The next Gen Z tenet is compatible. We have to take IT customers and operators on a journey from legacy infrastructure to next generation infrastructure possible with Gen Z technology. This includes the ability for Gen Z infrastructure to support existing operating systems with no modifications except for perhaps new drivers. Furthermore, a graceful interconnect transition from PCIe to Gen Z would also make for a smooth transition to Gen Z. The next few slides demonstrate how Gen Z's architecture enables a smooth, frictionless transition to Gen Z-enabled infrastructure. First, let's look at block storage support for Gen Z components. We can have Gen Z SSDs that operate almost exactly like NVMe drives from a software and driver perspective. See the block storage tutorial video for more information. We will call them NVMe drives. These NVMe drives take advantage of Gen Z's logical PCI device or LPD capabilities, which we will describe more in a moment, that allow unmodified operating systems to use their PCI discovery algorithms to discover and boot from these NVMe drives. From the figure on the right, one can see that Gen Z block drivers, the red box, fit into the storage stack where traditional storage drivers operate. The Gen Z driver communicates through the Gen Z hardware interfaces to the NVMe drives on the fabric. Now, let's look at how Gen Z-enabled storage class memory is supported under unmodified operating systems. As mentioned in the high-performance portion of this video, operating systems have been adding support for direct access to persistent memory-based file systems over the last couple of years, primarily to support emerging non-volatile DIMMs or NVDIMMs technology. The recently developed persistent memory file system, also known as the direct access file system, allows the use of special APIs between the applications and the persistent memory file system to directly access file data in a byte-addressable manner using CPU load store instructions by mapping the file data into the application's memory space. The persistent memory file system is designed to work hand-in-hand with a block driver for the persistent memory so that traditional block storage APIs and applications can also access the data in the memory devices. So here's the really good news. Gen Z-enabled storage class memory can completely leverage this entire stack of software to enable both traditional block storage access as well as the new persistent memory file system enabled applications by simply providing a Gen Z storage class memory driver in the software stack. This is illustrated in the figure to the right. Finally, Gen Z enables messaging between Gen Z-enabled CPUs using existing APIs and software stacks. Gen Z supports the concept of an emulated Ethernet NIC or ENIC drivers that facilitate tunneling Ethernet packets over Gen Z. The ENIC driver sits in the same place as a traditional Ethernet driver would in the TCP/IP communication software stack, as illustrated in the figure to the right. The ENIC driver accepts Ethernet frames sent down from the stack for transmission and utilizes Gen Z hardware capabilities to segment the packet into smaller Gen Z packets transmitted across the fabric. Likewise, the Gen Z hardware and ENIC driver receive encapsulated Ethernet Gen Z packets from the fabric and reassembles them into Ethernet packets and sends them up the protocol stack. This enables traditional applications designed to communicate over the Sockets API to continue to benefit from the compatible communication models across Gen Z fabrics. A CPU can also send encapsulated Ethernet packets to Ethernet gateway components that convert the encapsulated Ethernet packets to raw Ethernet packets for transmission on standard Ethernet networks for communication with native Ethernet devices. Likewise, the right-hand side of the diagram depicts the use of Gen Z in a high-performance computing software stack using the Open Fabric Interface, or OFI, API and libfabric framework with a Gen Z driver to support the HPC middleware, like Message Passing Interface, or MPI, partitioned global address spaces, or PGAS, etc. Using Gen Z's optimized op-class request responses for atomics, collectives, and RDMA-like buffer ops, feature-rich HPC messaging implementations are readily achievable. Viewers can learn more about Ethernet-compatible messaging and low-latency HPC messaging from the use case videos that are part of this video tutorial series. Gen Z enables storage class memory, and CPUs with Ethernet-compatible or low-latency HPC messaging can support unmodified operating systems while taking advantage of most of the awesome features and benefits of Gen Z described in this video. We mentioned Gen Z's logical PCI device or LPD feature in the last slide. Let's take a closer look at this feature. Gen Z's LPD utilizes two capabilities illustrated in the figure on the right. The first is the component PCI structure that is in the Gen Z control space of any Gen Z component that wants to be discovered as a PCI endpoint by a host component like a CPU. This structure instantiates the PCI configuration space of the equivalent PCI endpoint. For example, a Gen Z NVMe drive or SSD drive that wants to be discovered by the host CPU's operating system as an equivalent NVMe drive would implement the component PCI structure in its Gen Z control space. The second LPD capability is the PECAM logic block in the Gen Z enabled CPUs. On CPU boot reset, the BIOS or system firmware will perform Gen Z device discovery, and for each Gen Z component discovered with a component PCI structure, would map this into the CPU's PCI bus architecture and program the PECAM logic block to enable standard PCI bus discovery of the Gen Z components using PCI bus device and function numbering. We will morph the figure to the right to illustrate how the Gen Z devices appear to the operating system or system firmware's PCI discovery process. As you can see, the arbitrary Gen Z fabric topology is flattened to make it appear all Gen Z devices are tied to a single PCI bus segment. In addition, only Gen Z devices that have a component PCI structure are discoverable by a standard PCI discovery algorithms. For example, the GPU on the far right is not discovered as a PCI device because it did not contain a component PCI device structure. Gen Z's LPD also enables booting from these devices. A more in-depth use case video in this series provides more details of Gen Z's LPD feature for viewers that are interested. Another feature is Gen Z's PCI compatible ordering feature, which enables Gen Z to maintain strict transaction ordering similar to PCI Express to ensure complete compatibility with PCI Express device drivers. This feature is coupled with the Gen Z LPD feature we just discussed. Gen Z end-to-end protocols are powerful and don't mandate strict ordering like PCI protocol does. But if you need strict ordering to ensure existing device drivers for PCI Express equivalent Gen Z devices operate correctly, then Gen Z offers the PCO feature. For example, if we want a Gen Z NVMe drive to behave exactly like a PCIe NVMe drive, then we would enable PCO to ensure absolute compatibility with the existing NVMe drivers operating over the NVMe drives. Gen Z's ability to support a PCI Express compatible physical layer allows CPUs to be designed with interfaces that are bimodal and operate as either PCI Express or Gen Z links to the rest of the system. This facilitates a graceful migration path from PCI Express to Gen Z. Look at the animated figure to the right that illustrates a progression of a system from a PCI Express only configuration to a mixed PCI Express and Gen Z configuration, and finally to a Gen Z only configuration, all while using the same CPUs but reconfiguring a subset of the links on each iteration. The gold links in gray slots represent PCI Express, and the red links and slots represent Gen Z. The progression can be achieved by using different risers in each iteration that change the slots from legacy PCI Express CEM connectors to Gen Z optimized connectors based on the TE sliver technology. Another possibility could be if the PCIe standards body, or PCI SIG, adopted the same TE sliver connector used by Gen Z with compatible electrical and mechanical specifications for use on PCI Gen 5 capable slots. If this happens, the same riser will work for both PCI Express Gen 5 and Gen Z link configurations and allows the system to dynamically configure the links as PCI Express Gen 5 or Gen Z based on the option cards that are plugged into these slots. This capability facilitates a smooth, frictionless adoption of Gen Z technology when IT administrators and data center operators are ready to adopt Gen Z technology. The last Gen Z tenet is economic. The design of the Gen Z architecture strove to achieve significant economic value from infrastructure built with Gen Z as a foundation. Whether it's more workloads with an equivalent amount of infrastructure or being able to perform the same workloads with far less infrastructure, Gen Z provides numerous advantages to achieve both. First, Gen Z's adoption of leading industry standard high performance serial physical layers leverages high volume silicon libraries, which in themselves drives lower cost. In addition, using this technology enables Gen Z components to benefit from levels of pin efficiency not found in today's components, making them smaller, easier to manufacture, and lower cost. This also leads to the printed circuit boards that these components are mounted on to be easier to design and manufacture, further reducing costs. Look at the figure on the left. This is a state-of-the-art CPU, GPU, or system on a chip with 8 DDR memory channels and upwards of 64 or more PCI Express lanes. You're looking at a device with well over 4,000 pins. 50% of those pins are just for the DDR memory channels, including power, ground, control, and data pins. The figure in the middle illustrates the pin efficiency of DDR5 memory channels versus Gen Z interfaces at numerous data rates. Pin efficiency is the bandwidth of the interface divided by the total number of pins instantiating that interface. The pin density of a DDR5 channel at 4,400 mega transfers per second is about 0.55 gigabytes per second per pin, while the pin efficiency of Gen Z at 32, 56, and 112 gigatransfers per second is 4, 7, and 14 gigabytes per second per pin, respectively. Obviously, a significant improvement. What this allows us to do is build new CPUs and GPUs and system on a chip with 4x to 8x the bandwidth, with 50% fewer pins dedicated to memory. This is illustrated in the figure on the right. This allows us to lower the device package costs and dynamically simplify the PCB design and lower overall system costs. Gen Z helps us to alleviate some of the stresses that our two-socket server we discussed in Gen Z, the New Approach introduction video series, experienced. Let's revisit the TE sliver connector family, as this component of the Gen Z architecture also helps drive value and lower costs across the industry. Not only does TE sliver family of connectors allow different form factors to be supported, the exceptional electromechanical properties of these connectors are motivating other standards bodies to consider pin-compatible versions for other applications, like SSD and disk drive connectors and components, as in the SNIA SSF and the EDSFF forums. Future versions of the PCIe CEM or or common electromechanical connector in the PCIe special interest group, and for OCP mezzanine cards and other applications within the Open Compute Platform community, OCP community. And finally, for next generation memory connectors in the JEDEC standards body. If a common connector system and pinout can be achieved across all these applications, standards bodies, and consortium, this will drive high volume and lower costs across the board. In addition, these connectors are optimized for high pin density, smaller layouts, higher bandwidth per pin. In the figure on the right, you can see the size and aggregate bandwidth comparisons between a variety of legacy connectors and the TE sliver variants. Lower costs, smaller size, better performance. Now that's a winning combination. Finally, Gen Z is economic in its ability to deliver right-sized solutions. What we mean by that is that Gen Z allows us to do for physical infrastructure what we've been doing with virtualized servers under hypervisors over the past decade. Now, instead of having fixed server configurations with static CPU, memory, I/O allocations, Gen Z enables truly disaggregated infrastructure where CPUs, memory, storage, accelerators of all types can be composed into logical systems to apply to any workload. As seen in the figure above, Gen Z fabrics enable fabric-attached DRAM and storage class memory, CPUs of any size and computing capacity, accelerators including GPUs, FPGAs, DSPs, custom ASICs, and storage accelerators that support rich data services, SSDs and NVMe drives, and gateways to legacy storage and networks. This architecture enables us to partition the infrastructure to create logical systems and servers that are tuned specifically for the targeted workloads. As you can see in the animated figure, we can create logical web servers that are with moderate CPU, storage, and memory requirements, as well as access to network gateways to allow communication with external client networks. We can create a logical database server with large memory, high CPU compute capacity, large storage class memory capacity, and access to traditional disk drives for capacity expansion. We can create a logical analytics server, which needs different types of analytic engines or accelerators for performing machine learning or analytics algorithms, and lots of memory for memory-centric computing. And finally, we can create various logical storage systems. Let's say a moderate amount of CPU and DRAM, a large capacity storage class memory to support in-memory databases, key value stores, or object storage systems. It can even be possible to build enterprise class storage systems in the same manner. This architecture helps us reach a point where over and under provisioning of infrastructure to workloads is a thing of the past. As the number of workloads increase, specific physical resources can be added instead of in a coarse-grained granularity of the past. If you need more memory, you no longer are required to add additional CPUs as well. The really cool aspect of this architecture is that the resources themselves can be partitioned into even finer grained provisioning. For example, you can still use cores of a CPU as virtualized servers. You can provision portions of a DRAM or storage class memory component to various workloads. What Gen Z is really enabling is a vision of what composable infrastructure should ultimately look like. The bottom line is that Gen Z is economic because it really does right-size infrastructure for the best possible business outcomes. We would like to invite viewers to take the next step in your journey to discover Gen Z by watching the next set of episodes of this series that cover example use cases for developing Gen Z-enabled components and systems. These episodes include DRAM and SCM memory use case, a low-latency messaging use case, a logical PCI device or LPD use case, a compatible Ethernet messaging use case, block storage use cases, and a data-centric computing use case. We hope you enjoyed this episode of the Gen Z tutorial video series, and thank you for joining us.